So let's move to the second source of difficulty, and this is the round off error. And the round off error, as we said, is because of the bounded representation. So how do you represent real or rational numbers? Well, the idea is to use what is called floating point, right? So you may have heard the term floating point. So what floating point says is that you basically have a sign. Okay, so this is going to be plus or minus. Okay, then you have an implicit decimal point, and then you have what is called the mantissa. So this is the accuracy of the number that you have. So you have some digits. So we will look at an example in a minute. So you have some p digits, and then you have an exponent, okay, which is another number. And there is an implicit base. Right? So for instance, normally when we do calculations, you might write, for example, Avogadro's number as 6.02 times 10 to the power 23. Now if you wanted to represent it like this, you would first have to move the decimal point to the beginning. Right? So you will say this is plus, okay, and this is 0.602, and the implicit base is 10, right? And the exponent is now not 23 but 24, because we move it there, you have to shift it one more time. So this would be a representation in this bounded form for this floating point number. So the point about the floating point is that this decimal point will now shift left or right depending on how you multiply it by this. Right? But now the problem with this whole representation is that you can only remember a certain number of digits. So if you have a number which has no finite representation like pi, or square root of 2, which is irrational, then you can only truncate it to p digits and the remaining information is lost. But even for other numbers which are not irrational but numbers which have recurring decimals, like 1/3 in decimal, it's 0.33, or 2/3 is 0.6666 indefinitely, you have to truncate it at some point and either round off the last digit or just drop it off or something. Right? So of course typically computers will not use decimal but will use binary, right? So you will have p bits, right? And the implicit base is 2, but the principle is the same. So now usually most computing platforms will offer you a trade-off of accuracy for speed. Now if you use more digits in your computation, it's slower. So basically you have more precision, or more accuracy rather, means slower. Okay? So you will have different types of representation. So the basic representation is usually called single precision, right? And if we translate it to decimal digits, it means 7 or maybe 6 digits after the decimal point, right? So remember that our mantissa was of the form dot, d1, d2 up to dp. So what this means is that if I'm thinking of this as a decimal number, then in single precision p will be 6 or 7, right? And then the next thing is called double precision, and this is usually twice as many digits, 13 or 14 digits. And then there is something called extended precision, which is about 3 times as many as the original thing, so it's something like 19 or 20 digits, right? So depending on how much of a problem it is, you might move from a single precision representation to a double precision representation, but then correspondingly every computation will be slower, so you have to trade off the accuracy of your representation with the speed of the computation. So we need some kind of a notation or some convention as to how we are going to measure off the round off error. So usually if we have a value, say alpha, that we are trying to represent, then we use alpha star for the actual numerical value. That is, this is the mathematical value. Yeah? And we use the alpha without the star for the representation. This is the bounded finite representation that we have using our floating point mantissa and exponent representation. So what we really want is the difference between these two, right? So if we are just looking for the absolute error, is just the absolute difference between alpha star and alpha. But very often it's not the absolute error but the relative error that we are interested in, right? So we are interested in how much this is as a fraction of the value alpha star itself. Right? So this is the relative error. So the absolute error is just the difference between the mathematical value and the represented value, and the relative error is this difference normalized to the absolute value. So there are two basic kinds of errors that come in when you're doing rounding off. So one is overflow. So the value in an overflow is too large to be represented. So you just don't have enough digits in your exponent to write out the value. So there are some ways to fix this. So one solution is sometimes your computation, if it is going to result in an overflow, you can avoid the overflow by reordering the operations. Okay. So consider something like 10 to the power 29 times say 11 to the power 30 divided by 12 to the power 30. Now if you take the numerator, then you get some large value with an exponent of 60. But if on the other hand you do it as 10 to the power 29 and then you reorder this as say 11 by 12 to the power 30, then you get a number which is close to 1 raised to the power 30, which will not be a very large value, and then you multiply this. So these two are equal expressions, but they are not equivalent in terms of how they overflow, because this numerator will overflow and this will typically not overflow. The other possibility is to actually use alternative formulas. Right? So if you want to compute say 100, choose 2, right? So the naive computation says that this is 100 factorial divided by 2 factorial times 98 factorial, right? Now 100 factorial, 98 factorial are very large numbers. So if you actually explicitly compute them, you will have an overflow. But you know that in this there's a lot of cancellation, because 98 will cancel out 98 factorial on the top. So actually this is only 100 times 99 divided by 2. So this is a very simple number, but if you compute it explicitly using large factorials, then you're going to get an overflow. So it's better to do some mathematical manipulation to get the most optimum way to compute the given formula. Right? And then the third solution is sometimes you just cannot do much. So you just reduce everything by working with logarithms, right? So instead of working with the actual numbers, instead of doing x times y, right? Instead you will do log x plus log y, right? So everywhere where you're dealing with very large or very small numbers, if you take logarithms, then all multiplications become additions, and it's much easier to work with these values without getting overflows. So at the other end of the spectrum, there is something called an underflow. And this is a value that is too close to 0. So you want to have a negative exponent. So you want something like 0.2 times 10 to the minus 500. But this number the exponent is too small, you can't store it. So this is a very small number, and then it will become like 0. So typically what happens in these kind of things is that the computation continues with the value 0. So you have a non-zero number, but you can't represent it. So you'll just treat it as 0 and continue. But you will mark some kind of a flag indicating there was an underflow, so that later on, if you find some unexpected calculations, you know that there was a step in between when some undesirable approximation happened in this case. Because for example, supposing you're dividing by something and you set it to 0, you're of course going to get into problems. So underflow will typically leave 0 in the computation and proceed. It's not like overflow. If you do an overflow, then you're stuck. You don't know what to do because you have a number you can't represent. Here you can approximate it by 0, but you mark that this is an error so that later on you can come back and trace where the error occurred. So one thing to keep in mind when we are working with these finite precision representations is that arithmetic operations are never exact. And what this means is that we could have some errors which arise because of two approximate values being close to each other. So supposing, the problem is called subtractive, let's write that properly, subtractive cancellation, right? So subtractive cancellation happens when you subtract two numbers that are close to each other, and then each of them might have a good relative error, but the subtracted value might be bad. Right? So here's an example. So supposing I want to represent the value pi. So if I represent it, So supposing I'm using single precision, so I have 7 decimal digits, right? So I write pi out to 7 decimal digits, so 3.14159.2. So I've used up now 7 decimal digits. Now if I continue a little more, the next 2 digits are 6 pi. Okay, so this is my pi. Now if I make a change beyond this, so supposing I now put b star is pi minus 6 times 10 to the minus 7. What this is going to do is going to knock off this digit, right? 6, 1, 2, 3, 4, 5, 6, 7. So this is going to be 3.14159.205 dot dot dot, right? So now it turns out that if I actually compute these relative errors, a star minus a divided by a star and so on, or these two relative errors, okay, so these are approximately of the order of 10 to the minus 7, which is very acceptable if you have 7 digits of precision, and 10 to the minus 7 is your expected error. But now if I compute C star, which is A star minus B star, so notice that in the first 7 digits they are identical. So the first 7 digits will go to 0, and I'll have a number which is of the form 0.12345 and then here I will have 6 and then I will have 0. Okay, so I have this. But now if I look at the representation of C in this thing is going to be 0. Okay? So C is actually going to be close to 0 at least. And so in this case you can actually compute that if I look at C star minus C divided by C star, this is actually going to be something like 2/3. Right? So from 10 to the minus 7, the relative error has jumped to 2/3 because we took two values which are very close together and we subtracted them. So this is the problem of subtractive cancellation. So one of the difficulties with these round off errors is the errors cascade, right? So early errors are propagated to later stages. So what might happen therefore is that at a later stage the numbers might numbers in the computation might change slightly. Right? And sometimes this might drastically affect the answer. So these are such problems where changing the numbers in the input slightly drastically change the output are called ill-conditioned. So here is an example of an ill-conditioned problem. So supposing we have two simultaneous equations of this form. So 1.001x plus 0.999y is equal to 2 and 0.999x plus 1.001y is equal to 2. So this you can work out quite easily as a solution where x is equal to 1 and y is equal to 1. Now suppose this value is perturbed slightly, the right hand side. So instead of 2, I say that this is, say, the first equation is now of the form 1.001x plus 0.99y is equal to, say, maybe 2.002 and 0.999x plus 1.001y is equal to 1.998. So the point is that this answer, this 2, could be coming from an earlier stage in the computation. So instead of an exact 2, I get some rounded off value which is, say, correct to 3 decimal points. So now this computation will be affected by the fact that the right hand side of the equation came from an earlier stage with some error. And now if you compute the values here, suddenly from x equal to 1, y equal to 1, you get two new solutions, a new solution, two new values, x equal to 2 and y equal to 0, which are drastically different. Right? So this is an ill-conditioned equation. By changing some of the parameters in the equation, the answer moves around drastically to a different point altogether. And this is something that arises because of cascading errors, and this is something we have to be aware of.